Hello everyone, my name is Leonardo, and today I will present our work Smelting Gold and Silver for Improved Multilingual AMR-to-Text Generation. This is a joint work with Jonas Pfeiffer, Yui Zhang, and Irina Gurevich. So in this work we explore AMR. AMR stands for Abstract Meaning Representation. This is a semantic formalism that represents the meaning of a sentence. So here you have AMR graph, and here you have the sentence that describes the meaning of this AMR. In this work we are interested in AMR-to-Text generation. This is a task of producing a text which verbalizes the meaning coded by an input graph. So usually you have an input graph, you train an encoder-decoder model that generates sentence based on this graph. This is a challenging task because a model needs to encode the complex structural information of the graph in order to generate the text. Usually what we do is we linearize the graph in a sequence of nodes and edges in order to train those models. In particular, in this work, we are interested in multilingual AMR-to-Text generation. This is an even more challenging task where you have an AMR English-centric graph here, and you'd like to generate sentence in different languages that describes the meaning of this AMR. However, we face some limitations in the multilingual AMR-to-Text generation. One problem is that gold standard multilingual AMR training data is currently scarce, and previous work has investigated synthetic generated AMR as the only source of silver training data. So our goal here is to answer this question: how can we cheaply acquire silver standard multilingual AMR-to-Text data? We investigate three approaches. First, we parse English sentence into silver AMRs from parallel multilingual corpora. We call this approach silver AMR. Second, we translate English sentence from gold AMR-to-Text corpus to the respective target languages. We call it silver sent. Finally, we investigate a combination of these two sources, silver AMR and silver sentence, in a multi-source scenario. So we explore two data. The first one is the LDC 2017 T10 dataset. This is a dataset that contains English AMR graphs and English sentence. So we call it gold AMR because those AMRs were annotated by humans. We also use parallel data from English to other languages, namely Spanish, Italian, German, and Chinese. So given these two sources of information, gold AMR and parallel data, we would like to explore different data augmentation strategies in order to train multilingual AMR-to-Text generation models. For silver AMR, we generate about 2 million silver AMR graphs from parallel corpora using a state-of-the-art AMR parser. In this setting, for each data point, we have a silver AMR and a gold sentence that describes this AMR in different languages. In the silver sent approach, we fine-tune an MT5 model as a translation model for English to the respective target language. After, we translate English sentence from gold AMR into the respective target languages. So in this setup, we have gold AMR structures, but silver sentence for each data point. So our approach fine-tune MT5 model, and for that we linearize the AMR graphs using the Payman notation. So here you can see a AMR graph together with its Payman notation, and we also add a prefix to guide the model to generate the sentence in a desired language. In this case, we'd like to translate this AMR to Spanish. In this setup, the encoder is required to learn language agnostic representations, and the decoder is required to generate a text in different languages. We evaluate our models on the multilingual AMR corpus, namely LDC 2020 T07, and we compare with previous work using blue and bird score. First, note that silver sent outperforms silver AMR. We think that the reasons are the following. First, correct semantic structure of the gold AMR is necessary for faithful realization. Second, silver sent provides examples of the same domain as the eval test set. We also see that the performance of silver AMR plus gold AMR is comparable to silver sent. This suggests that combining target domain data plus gold AMR is necessary for downstream task performance. And finally, when we combine silver AMR plus silver sent, we achieve the best results, showing that these two sources of silver data are complementary. Finally, when we add gold AMR, it does not lead to any notable gains. So overall, our results demonstrate that both gold AMR and gold sentence are important for training a strong multilingual AMR-to-Text model. Further, we investigate the effect of fine-tuning order. So we compare our multi-source scenario with a sequential fine-tuning scenario, where we first fine-tune in one kind of data and later fine-tune in a second phase fine-tune in another kind of data. So the figure illustrates the performance, and first we see that there is a decrease in performance for all sequential fine-tuning settings. showing that our multi-search scenario leads to better performance in terms of blue score. We also note that combining silver AMR and silver sentences improve the performance even in the sequential fine-tuning. Here, we investigate the impact of sentence length and graph size in the performance of the models. Intuitively, silver AMR is potentially less capable of encoding the AMR semantic correctly, and silver sent potentially generates fluent sentence less reliably. In particular, we calculate the ratio of the sentence length divided by the number of AMR nodes, and you can see the results in this figure, where you have different languages and they approach silver AMR and silver sent. First, in silver AMR, the blue scores increase for longer sentence, so this suggests that longer gold sentences improve performance. On the other hand, in silver sent, the blue scores improve for large graphs. This suggests that large gold AMRs are important for the performance. So silver AMR and silver sent approach present relative gains in the performance in opposite ratios. So it suggests that they capture distinct aspects of the data, suggesting that these two different kinds of silver data are complementary. We execute out-of-domain evaluation. The goal is to disentangle the effects of in-domain sentence and gold quality AMRs in silver sent. In particular, we evaluate in a subset of the multilingual AMR corpora that the domain of the subset is not included on the training set. So first note that silver sent prevails in achieving better performance. That suggests that AMR gold structures are very important for training multilingual AMR-to-text generation models. However, the approach performs more comparable, demonstrating that domain transfer plays an important role in the strong performance of silver sent. Here we present a case study where you have a AMR graph and we have a sentence generated in Spanish language for different models. So note that silver AMR fails in capturing the correct concept prep it out, and this is related because a silver AMR is trained using noise graph structures, and these noise structures can lead to models less capable of encoding the AMR semantic. On the other hand, silver sent generates a grammatically incorrect sentence, so in this case generating kipodia, and as these models are trained in sentences that could be ungrammatical, these models can be less capable of generating fluent sentence. Finally, when we combine silver AMR plus silver sent, the model is capable of producing a more accurate output, generating grammatically correct and fluent sentence. So in this work, we evaluate different data augmentation methods for multilingual AMR-to-text generation. In order to do that, we explore two kinds of research: a gold AMR corpus plus parallel sentence from English to different languages. Our experiments showed that both sources of silver data, namely silver AMR and silver sent, are complementary. Our code can be found in this link. Thank you very much.